Thank you, Paul. It's a tremendous honor to be here in front of all of you. We're really excited to have you for QHack 2021. I want to begin by actually taking you back to the heady days of 2018. Now, back in 2018, it was a good year for superhero movies. We lost some great scientists. There were some notable world events. Kids all over the world were eating Tide Pods. It was a really hectic year. But as well, 2018 was the year where you can really say that the NISC era began. So you see this paper here from John Preskill, 1st of January 2018, really kicking off the NISC era. Technically, he had given a talk about a month earlier at QGB, but this is when the paper landed. And I remember this real switch where people just, this word wasn't in their vocabulary, and all of a sudden everyone was using it because it was exactly the word that was needed at the right time. Now, it was also a really, I would say, important year for QML. So before 2018, we mostly had QML, this idea that you were going to use fault-tolerant algorithms to run machine learning models like deep neural networks or invert linear systems or things like that. And there were some early hints before 2018, but really in 2018 was when I think the floodgates opened, at least in my mind. This is when a number of key papers started to come out, including some from our team and some from other teams, that really kind of shifted the thinking from what you could do with QML. And again, it's based on ideas that were appearing earlier, but this is kind of the year where it coalesced in my mind. In particular, I want to call out this paper, Quantum Circuit Learning by this team from Japan. This paper, it really caught my attention when it came out. And the reason it caught my attention is there's just like one section in it where it says something like, just by inserting plus or minus pi/2 rotation and measuring expectation values, we can evaluate the exact gradient of an observable. And this really caught my attention. And it's just a small piece of this paper. It's not the whole story of this paper. It's about quantum circuit learning. This is just one weird trick appearing in that paper. But to me, this was the one that really caught my attention. Now, why did that catch my attention? So I had actually been spending about a year at the University of Toronto in a group that was working on deep learning. So I have a quantum computing background, but I spent a year just unplugged from quantum. And so I picked up all of these ideas from deep learning. I was seeing things that have been working very well in deep learning and kind of ingrained in my consciousness. So it was bubbling around in the back of my mind when I read this quantum circuit learning paper. And for that, it was really, this gradients, quantum gradients. That's the idea that really caught my attention. The fact that you could compute the gradient of a quantum circuit, and this is something that Maria mentioned in her talk. If you can compute the gradient of a quantum circuit, then you can basically train a quantum circuit in the same way you can train a neural network. And the gradients it's not the only method you can use to train a circuit, but it's a really nice method. And it works very well in deep learning for various reasons, but it's kind of the most basic answer you could have if you have the question, how do I improve my model? I have some model that has some set of parameters. How do I tune those parameters to make it better? And you say, well, I have some cost function. And here I have a plot from one of my older papers when I was at the University of Toronto working on deep learning. This is a kind of sketch of how gradient descent works. You have some parameter space Z, and then you have some function of those parameters T, and that function defines a landscape. And that's the cost function. You want to maximize the value that you're at. So you want to choose the parameter Z that maximize the value of T. In this particular case, I was maximizing some DNA sequences. So in fact, this gradient descent isn't just used for neural networks. It can be used for pretty much any kind of computation you can imagine, as long as you can find the gradient. And in this case, I was looking at trying to maximize DNA sequences towards some particular purpose. And the really nice thing about gradients is that it can be completely automated. It's something that the user doesn't even have to care about. Modern machine learning libraries automate this process for you. And this is not something that we had available before that in quantum computing. So again, I spent some time working as a deep learning researcher, and I got used to these machine learning tools. In particular, I worked a lot with TensorFlow, but now as well, we have PyTorch and JAX that are quite popular, and we have some older libraries like Theano that really set the table. And you can think of deep learning software as, it does lots of things, but I would say there's kind of three key features that deep learning software brings to you. One is this notion of automatic differentiation. So I said gradients are very important for deep learning. What automatic differentiation does is it finds those gradients automatically for the user. The user doesn't have to say, here's my function, and here's its gradient. It just has to say, here's my function. And the gradient comes automatically via an algorithm. So that's the feature of automatic differentiation. And it can really reduce the time to build and train models because it's all automated for you, and it's less error prone than a human doing it themselves. Another thing that deep learning software provides is the ability to run on specialized hardware, for instance, GPUs or TPUs. And I want to say we can go beyond deep learning. So deep learning was originally about neural networks, but in fact, the ideas of deep learning fill in this larger area of differentiable programming that Maria mentioned. And the idea of differentiable programming is you should be able to train any computation, not just a neural network, but any computation. So again, differentiable programming, for me, what it does is it kind of shifts our focus a little bit. So before you have a computer that can automate all of this stuff for you, all the gradient finding and the training for you, how do we find algorithms? Well, we find algorithms by experts handcrafting them. So in deep learning, before they had deep learning, they had image processing experts who had to design algorithms and had to design custom kernels for their image processing algorithms. So this requires a high degree of skill. It has to be very specialized. It can be slow because it's a human doing it by hand, and it can be repetitive and wasteful because you can make mistakes and it can slow you down. You can look at Einstein here. I mean, look at him. He's writing something on the blackboard here, but you can see the expression on his face, and he's thinking, "Did I remember to carry the 2?" So no matter how smart you are, it can be a slow process for an expert to handcraft models. So what differentiable programming allows you to do is just say, here is my computation, and all of the other stuff comes automatically. So I just say, I want a function that does X, and I write that function in code, and then I don't have to worry about the training algorithm or anything like that. I can actually discover different variants of my algorithm through optimization processes. This allows a rapid feedback cycle, and it also allows more users to get in and contribute to the field. It doesn't require expert skill. It just requires a little bit of programming knowledge and some mathematics sophistication. So going back to this paper, quantum circuit learning, the reason it blew my mind is because I thought, we now have a trick. We have one weird trick we can use, which has now become known as the parameter shift rule. This is something we can use to perform automatic differentiation of quantum circuits. So all the user has to do is tell me what their quantum circuit is, and software can automate the whole optimization process of training that quantum circuit towards some particular means. So that's why this particular paper, I want to call it out. It was kind of key in my mindset that this idea was opening up a new horizon. And right around that same time, we had the mission in our company to create a new quantum machine learning software library. And as you heard in Maria's talk, the original name was OpenQML. It's now called PennyLane, but the original name was OpenQML, which is maybe a bit too vanilla. But this is back almost 3 years ago, April 2018. These are my hand-drawn notes that I made to myself when we were in the very, very first stages of designing PennyLane. And you can see I've highlighted here one of the core features. Actually, it's all the core features that I highlighted at that time, is that first you want to be able to provide a device-independent syntax for programming different hardware or simulators. But more importantly, automatic differentiation of quantum circuits. In my mind, that was the key ingredient that we needed to really take QML from some expert thing to something that anyone could try out. That was the key feature that we had, even in its very, very first version of PennyLane. We built it around this key feature. So that was April 2018. By the end of that year, we had finished the first version 0.1 of PennyLane. And as you can see, even in the title, we put automatic differentiation of hybrid quantum classical computation. So really the whole beginnings of PennyLane was around this idea of automatic differentiation and differentiable programming. So by now, we actually have quite a few software packages in the same space. So we have PennyLane, which is the one that we've developed here at Xanadu. We have also TensorFlow Quantum. We have YAO, which is a Julia library. We have Tequila from the Matter Lab at University of Toronto. We have Hyrax from Racco. So a lot of all of these software libraries have representatives here at QHack. So you should be able to also ask them questions about their libraries, and you can see what they think about the field. So we've invited everyone here to talk about it. I know PennyLane the best, so I'm going to focus the rest of the talk on PennyLane, but everyone else during the week will have representation. So feel free to ask them questions when they have their talks. So this slide is actually going back to that previous slide when I talked about deep learning software. Now this is QML software, or larger picture, quantum differentiable programming. And I'm repeating the exact same headings that I had before. 3 features that are key. Automatic differentiation. You give me a quantum circuit, and I automatically determine which other circuits I need to run to compute the gradient. Run on specialized hardware. So instead of data centers with GPUs or TPUs, you're running on quantum computers, which are now becoming available. And again, this idea that you should be able to train any computation. If you can give me a native computation, in this case, a quantum circuit, then I should be able to train that towards some particular optimal configuration. So as I said, I'm the lead developer of PennyLane, and our team works on PennyLane, so that's the one that I know best. As well, we have the QML challenges that we've just opened up today, and those ones, well, you'll need PennyLane to code up those challenges. So I'm going to give you, in the rest of this talk, an overview of PennyLane so you know exactly the basic tools that you need in order to tackle those challenges. So PennyLane is a cross-platform Python library that focuses on this notion of differentiable programming of quantum computers. So you can actually just think of PennyLane as a general quantum computing framework. You can do any quantum computing task in PennyLane, but it has this differentiable programming built in by design. So not only can you create any quantum computation, but you can also train any quantum computation. And you can use exactly the same tools you would use to train a neural network. So again, if you're going to be tackling the challenges, there's a lot of variety there, but the main workflow for any QML problem has, I would say, 3 steps. The first step is declaring your quantum circuit, right? And this is where you would stop if you had just a kind of vanilla textbook quantum algorithms. You just have the quantum circuit and you would run it, and that would be it. But in QML, we do something slightly more. We have a quantum circuit, and we also keep free parameters in that quantum circuit. And then we need 2 more steps. So we need a problem-specific cost function. So this cost function should somehow be a scalar function, so a single number, that quantifies how good your circuit is for a particular task, or even more broadly, how good your hybrid model is for a particular task. And then finally, once we have this cost function, we need to optimize. So we need an optimization procedure. So that's how a typical QML workflow or differentiable programming workflow extends your standard computation. Is first you make the computation, but then you also declare a cost function and you optimize it. So for those who are completely new to PennyLane, I can give you a hello world in PennyLane in about 15 lines of code. So the first thing in any Python program is actually just to do some imports. So in our case, we have to import PennyLane. And what we're going to do is we're going to use PyTorch as our classical machine learning framework that we're going to connect PennyLane to. We're also, in this particular example, this is kind of a historical example that we've had up on our documentation for quite a while. So it's an older Rigetti device. But we're going to use this forced QPU Aspen1 2QB device for this example. So this is just instantiating everything, just declaring I have a PennyLane computation, I'm going to use Torch, and I'm going to want to use this particular device. So I said on that previous slide, there's 3 steps. First step is actually just declaring your circuit. So here we have a very simple circuit, and it's not only a static circuit, but it takes in parameters. So you can think of it as a function. And in PennyLane, we declare every circuit as a Python function. And then you indicate which gates you want to apply in that circuit. In this case, we're going to apply the Rx and Ry gates, and we're going to apply them on the 0th wire. So it's a single wire computation, or a single qubit computation. And then, as with any Python function, you need to return something. So in this case, we want to say, let's return the expectation value of the polyz operator. So what this circuit does is it takes in 2 parameters, it does 2 rotations, and then it returns the average value of the polyz measurement, which is basically the z-axis on the block sphere. And then there's a final step, which is this decorator, this QNode decorator. And this is the thing that turns your circuit from a typical Python function into something that can actually be run on a particular quantum computer. So in this case, we're going to run on that device that we declared above. So then we want to build the cost function. I said this is the second step of a quantum computation with this differentiable programming mindset. So we want to say, let's take the expectation value of that circuit at some parameter values phi1 and phi2. And in this particular case, we're going to look at the mean squared distance between that output and the value -1. So when we maximize this cost function or minimize this cost function, it's going to put it as close to the value -1 or as far from the value -1 as possible. And then the final step is optimization. And actually, anyone who comes from a machine learning background, this optimization, if you look at it, doesn't have any quantum in it at all. This is a standard torch optimization workflow. So you have to declare particular variables that you want to use. And these are ones that you're telling torch you're going to optimize. You declare an optimizer, in this case, the atom optimizer. And then you do this optimization loop, and we do it for 300 steps. On the right side, you can see the circuit learning to put that state either as close to or as far to the value of -1 for sigma z as possible. And you can also see the cost landscape for phi1 and phi2, and you're finding different minima in that landscape. So how does this work? How does this work under the hood? So it seems like magic. You just declare a Python function, and you just add this QNode decorator, and you end up with something that can run on a quantum computer and be optimized end to end. So it's really kind of a neat method that we use, and it's basically relies on the fact that these deep learning libraries or these differentiable programming libraries, they allow you to define custom functions. And so long as you provide a gradient of that custom function, then it knows what to do. It knows how to optimize those functions, and it knows how to connect those functions to other functions in a larger workflow. So that's what we do with PennyLane is we take your circuit, which is a Python function, and we connect it to some instruction set that's going to run on a quantum computer or on a quantum simulator. And the only ingredients that are needed is some rule for evaluating. And this is typically just telling the device to run your circuit and give you the expectation value, and some rule for the gradient. And again, the gradient is something that's it's based on this parameter shift rule, for instance. And that's something that we can do automatically behind the scenes. So actually, let me just continue going back to the slide. So if you get something like a TensorFlow tensor or a PyTorch variable or something like this, we read PennyLane. What PennyLane does is it reaches in and discovers the internal numerical attribute of that object. So when it's called, it should have some value, and it just pulls out that numerical value, and it feeds that value to the quantum computer as whatever input is described in your quantum function that you've created in your code. The quantum computer runs, it might have to average the final measurement results, and then the value is returned. And that's just a function that takes classical data in and classical data out. And then all we have to do is wrap it back up in this tensor object, and everything works end to end. So it allows you to use TensorFlow or PyTorch or whatever you like as a driver for a quantum computation or a hybrid computation. So now I want to give you kind of a pretty quick overview of the features of PennyLane, because this should help you in some of the challenge problems. I noticed actually that there's one user who's already run the table, so that's really amazing that someone has claimed first spot on the leaderboard, but there's still plenty of positions up for grabs. And so if you look at some of these features of PennyLane, it should help you with some of the challenge problems. So first, starting at a very high level, PennyLane has a very flexible interface that integrates very nicely with the rest of the scientific Python stack. And it kind of works out of the box, so it's very useful for rapid prototyping. There's very little boilerplate required, just imports and declaring which device you want to run on, and that's basically it. You can immediately declare your circuit. So there's not really a lot of barrier in the way of rapid prototyping. As I said, all executions, all circuits that you want to run on a quantum computer are just declared as typical Python functions, which is how you would declare something in a neural network library or like TensorFlow or PyTorch. You would also just declare it as a function. And you just use this QML.QNode decorator to bound that particular function to run on a particular device. And then because they're functions, you can compose functions. You can take the output of a quantum circuit and feed it into a classical neural network. You could feed it into another quantum computer if you want. It can be arbitrarily composed. So the key ingredient that I mentioned a few times, and Maria also focused on in her talk, and actually you'll hear in the next talk from Krista as well, is this quantum gradients. And if you want, this can just be completely automatic behind the scenes. You don't have to know anything about it. PennyLane will take care of the gradients for you, which means that your circuits will be trainable by default. But if you want a bit more fine-grained control, we have a number of different options for how to compute gradients that work in different cases that are faster or slower depending on which kind of computation you have, or that are more or less approximate than others. So the standard parameter shift rule is the one that works on hardware. but we also can use backpropagation if you're working with a simulator and you essentially just use a neural network library to simulate a quantum computation. And then there's a few other methods like the adjoint and reversible method, which are more efficient than backpropagation, because if you know you're simulating a quantum system, you can take advantage of reduced memory. And then there's kind of an old fallback of numerical finite differences like you learned about in high school. Now, one thing I really want to emphasize, if you hear people talking about QML or variational algorithms, they'll talk about hybrid models. They'll say a variational algorithm is a hybrid model. And in some sense, this is true. But it's kind of limited in scope, I would say. So in a variational workflow, typically you have a quantum circuit, it has trainable parameters, and there is a classical computer present, but it's kind of like a passive driver of the computation. It handles the optimization, but it's not itself trainable. And we know that classical models like neural networks are, they can be gigantic and they can be very complex and they can be trainable as well. So my picture of a hybrid model is actually like, why would I stop the power of the classical computer as well? You have to be careful that you're not attributing quantum advantage if you've got a classical model in there, but you can also use the best of both worlds. You can say quantum computer is good at certain subtasks, and classical computer is good at other subtasks. If I have a larger computational pipeline, I can use them both, and I can make them both trainable. And this is something that's supported out of the box in PennyLane, is that every computation, including both classical and quantum components, is trainable out of the box, is end-to-end differentiable, and arbitrarily composable. PennyLane also works with pretty much any framework. You can just declare the circuit once, and it's a one-line change to run on multiple different hardware devices or simulators. So for simulators, we have a number of built-in simulators and simulator families for different use cases, and these are focused on rapid prototyping. If you want to start running on different quantum computers, then we have access to all of the popular SDKs and platforms. So whatever your favorite platform is, whatever platform you have access to, you can pretty much declare it once in PennyLane and run on all these different backends. You have to be a bit careful, so some of them use slightly different models, but as long as you're paying attention, you can use all of these different backgrounds interchangeably, or you can even combine different backends together into a larger computation. We have integration with higher level abstractions from the machine learning library. So we know that there's Keras layer. This is actually one of the most popular features of PennyLane, is to be able to just completely abstract a quantum circuit. It's just another layer in a larger computation. And this is something that users really like to do. So we have this Keras layer, and also the equivalent is the torch.nn module. So you can basically drop in quantum computations into a larger pipeline with no trouble. We also here at Xanadu have a big focus on quantum chemistry. And so we've actually built in a client library on top of PennyLane that focuses directly on quantum chemistry. So in standard VQE, you're typically given a Hamiltonian to begin with. But in real quantum chemistry, you don't start with a Hamiltonian. You don't start with an observable or measurement. You actually start with some atomic species and the locations that they're at. And from that, you have to derive to get to the point where you have this Hamiltonian. So this is what PennyLane QChem lets you do. It allows you to start from your standard chemistry data format and run the whole pipeline to get yourself into the state where you can run those computations then on a quantum computer. Another really cool feature of PennyLane, and actually one of the challenge questions is related to this, is that we have quantum aware optimizers. So the idea of a quantum aware optimizer is that it's nice that you can actually use classical machine learning libraries and classical optimizers out of the box to optimize quantum circuits, but they're a bit dumb. So they're designed for neural networks, essentially. So they don't know about the intricacies of quantum mechanics. So if you actually take that knowledge that you have about quantum mechanics, you could potentially make your optimizers more efficient. So for instance, there's quantum natural gradient. And what this does, it accounts for the inherent geometry of the quantum systems, which is different from the classical geometry you would get if you were using, for instance, neural networks. There's also what are called Schotz-Frugel optimizers. And the idea here is that running on quantum computers is expensive. It's either expensive in your wallet or it's expensive in your time because you have to sit in a queue. So you want to really save the Schotz budget that you have to run on the quantum computers as much as possible. And those are called shots frugal optimizers, and they're again compatible with PennyLane. We also have really quantum-specific optimizers like rotosolve and rotoselect. These ones are a bit different. They actually don't use gradients, so you don't need to use gradients. You can actually use any optimizer. But in particular, rotosolve and rotoselect are gradient-free optimizers that look at the structure of the quantum circuit when they're trying to find the solution. So all of these quantum-aware optimizers are also compatible with PennyLane. Once you've gotten past rapid prototyping, you might actually want to start running some beefier computations. So if you tackle the QML challenge leaderboard and you're starting to think about your hackathon project for your team, where you want to really demonstrate your skill set and tackle a problem of your choosing on quantum hardware, then you might actually need to be more mindful about how you're running your computations, because simulating quantum systems is difficult. It is classically intractable as the number of qubits scales. And running on quantum computers, you might have to wait in a queue, or it's a precious commodity. So you have to be mindful of how you're using it. So what PennyLane also allows you to do to save yourself time and effort is to parallelize your computation. You can parallelize both classically and quantumly. So you could parallelize in a classical simulator, so things run faster in different CPU cores aggregating together, or you can even parallelize across different quantum computers. So you're somehow you have a multi-component quantum computing model, and you need to run many circuits. You can run those in parallel across many quantum computers as available. This is a really cool feature. This is again something that should save you some time and effort, but it's a more advanced feature. So it's not something that you might see as a prototyping stage, but you would definitely get into if you wanted to optimize your quantum computation. So typically a quantum computation, a variational algorithm like VQE, variational quantum eigensolver, you'll want to have the same circuit, but you're going to have to measure many different quantities at the end. And what you can do is you can actually be a bit smart here, and you can say, I can convert that to the exact same computation, but it runs on fewer circuits, but I combine the measurements together. And this is called grouping, measurement grouping, and it's also available in PennyLane. Really valuable feature. Kind of final features here just that might be useful. If you're used to working in another framework like PyQuil or Qiskit, you can actually load your previous code into PennyLane, and you can basically run that code directly as if it was a PennyLane program, and you can run it on any PennyLane compatible execution device. Finally, we have a number of templates. So if you don't know where to start, we have some pre-built circuits. So if you're trying to trying to find a nice ansatz for some of those QML challenge problems, check out some of our templates. They should help you with those challenges. You don't have to build it yourself. So that's it. That's a real summary of PennyLane. I encourage you to check out our website if you're tackling those QML challenges and you're stuck at how to proceed. The best place to do is to check out our website. Click on the Learn button there, or on the Play button. You can find lots and lots of materials about how to get into quantum machine learning from the beginner level and more advanced as you're tackling those challenge problems. And as I said, we have tons and tons of tutorials and demonstrations on the website. So feel free to check them out. They all have code coming with them, and you can adapt those to your solutions for the QML challenges. So I want to finish with this one slide. This is actually something submitted for our meme contest. And I remind you all to submit on Twitter your quantum memes. We'll be judging them during QHack. This comes from my former colleague, Marco Piani, and his meme entry was, "One does not simply train quantum algorithms." So I just spent 25, 30 minutes telling you how to train quantum algorithms automatically using PennyLane. But the point of this meme, what I really want to emphasize is this is just scratching the surface. So we're putting the tools in your hands. So you now have the hammers, the saws, the screwdrivers, but those things don't build the house for you. You still have to figure out, there's still a lot of work to do for us in the field. So we still have to use these tools that have made our life easier to discover the interesting quantum algorithms, to discover the amazing training optimization algorithms, to discover the most powerful circuit structures. So it's really just, we're putting the tools in your hands that will make things accessible. And it's now up to you to figure out, or to the whole community actually, to figure out how we can best use these tools to get where we need to go, which is to build quantum computers that are powerful enough to tackle really interesting problems. So I really thank you for your time here. This has been really fun, and that's it. So Paul, I guess back to you.
Yay, thank you so much, Nathan. That was fantastic. I hope people don't take the silliness of that meme to overshadow the seriousness of that statement about these are tools and tools don't do things. People do things with tools. I really like that that sentiment. Couldn't agree more. So I mean, right out of the gates, biggest, most important, pressing question: PennyLane 2.0. What Beatles song would you use to name PennyLane 2.0?
I'm gonna go with one that I know you'll like, Paul. I'm gonna go with Silver Hammer
I love it. I love it. Why?
from
What makes you say that?
Maxwell's Silver
Maxwell
Hammer.
Silver. I like it. Yes, yes. It's actually a little. Look at
Yeah,
this. I could even do the
swag is
double
pretty
hat.
neat.
The little, yes, the swag is strong with this one. I want to show off my lovely QHack mug, but I drank all my coffee, and so now it's lost its secret look. Next coffee, I'll show it off for everybody. So much great swag. Um, yeah, that's fantastic. So you don't forget with that meme competition too. There's some swag coming out for the best memes. So keep getting those in.
We
Um,
got some good ones
uh,
so far.
yeah, I've seen them. I've seen pretty much all of them. They are quite good. I'm really impressed with the people's meme game. So maybe a bit more serious note. Some questions from the chat on PennyLane. I was curious about this too. Can you integrate PennyLane and Torch with PyTorch Lightning?
PyTorch Lightning. I don't know what that is. I have to admit my ignorance here.
No problem. Well, we
So
can save that one. Josh might be able to weigh in on that.
maybe someone in the chat can answer that one. I spent so much time in quantum land that I've actually, I did say I spent time as a deep learning researcher, but I have to say that my skills are not sharp anymore. So it's more focused on the quantum side these days.
No problem. Okay, so how about this one? All right, another question from the chat on PennyLane. Did you consider gate noise or low qubit fidelity for backpropagation?
For backpropagation, so the way backpropagation works is it's what you do, and it's only actually compatible on a classical computer, is you run a computation, and at every step of the computation, you store a value. And then at the end of the computation, you have the final value, but you want to compute the gradients, and it's called backpropagation. So what you actually do is you step backwards through that same computation. You look at those stored values that you did from the forward pass, and you use that to build up the final gradient of the it's called the backward step to compute the final gradient, and that gives you both the evaluation of the function and the gradient of the function. Now, backpropagation is a classical algorithm, so if you were actually to try and run backpropagation on a quantum computer, you wouldn't be able to store those intermediate states. So that becomes an issue. So you technically can't use backpropagation inside a quantum circuit unless you are using a simulator. So if you're using a simulator, then you're able to simulate it and you can store those intermediate state vector values. But if you're running on hardware, you can't do that. So if you're actually going to run backpropagation on hardware, what you have to do is you have to draw a box around the entire quantum circuit, and you can't kind of peek into that during the backpropagation algorithm. But that's what PennyLane does, is it uses this parameter shift rule to actually compute the gradients in a different method. So the question actually was about noise. And the thing about backpropagation is you could use it in a noisy system, and what you'll end up there with is just a stochastic estimate for the gradients. So stochastic estimates of gradients are actually useful. They are things that can be used to speed up training. It's well used in both deep learning and also in quantum machine learning. So noise in particular is not necessarily a problem unless it becomes either too large, that your computation is basically low fidelity and you're not really probing the Hilbert space properly, or the noise is biased in some way, then you're going to have a biased gradient. So you can use still backpropagation on or gradient-based training on a noisy circuit, but it depends on the quality and the type of the noise, whether it's going to be useful or not.
Wow, very detailed answer. Thank you.
Very,
That was
yes.
fantastic. Hopefully that that solved the question for the asker. So we got Maria to the rescue here. So PyTorch Lightning is a high-level PyTorch library. So I suppose it should be compatible. I'd love to see somebody submit a community demo for using PyTorch Lightning with PennyLane. I think that would be great.
That'd be awesome. The one thing about PyTorch is that they don't properly support complex numbers enough for us to build native simulators in there. So they're working on it for sure, but our PyTorch adoption has always been a bit slower than our TensorFlow or NumPy adoption because the support for quantum for complex numbers wasn't quite as strong as we needed it to be.
Oh, interesting. Cool. Did not know that. So let's see. Let's maybe move to some more general questions coming in from the chat. So can the input data for QML be quantum?
It can, yeah, for sure. And it can be quantum in two senses. So you can have quantum states being the input data. You have to be a bit more careful about how you consider input data there if you're using PennyLane, because you obviously can't pass a quantum state through a Python program. So you have to be more mindful about actually preparing that quantum state in your circuit. But you can use quantum data. You can also take quantum correlated measurements, so measurements that are the output of a quantum circuit that show statistics of entanglement or superposition. You can use that as an input to, again, a quantum circuit if you'd like.
Okay, makes sense. Another actually more general question. So, does automatic differentiation work for any kind of function that we code in PennyLane?
That's a really good question. So any kind of function. So automatic differentiation doesn't work for any kind of function in the universe. It works for deterministic functions or good approximations to deterministic functions. But if you have something that's a function like a random number generator, so it just spits out a random number every time, and that's not a deterministic function, then you can't actually use, there's no gradient. There's no well-defined gradient of a process like that, a stochastic process. So for instance, if you're using PennyLane to sample from a quantum circuit, which you can do, then you can't compute a gradient of that. But if you take those samples and you average them, which is what the expectation value is, then that is actually a deterministic quantity, and you can use a gradient there.
Okay, so we've heard a lot about gradients, and I get another question from the chat asking about alternatives to gradients for optimizing circuits, like, for example, using genetic algorithms.
For sure, for sure. So the way we built PennyLane is actually it's compatible with pretty much any optimization library you might like to use. We focus on gradient-based algorithms because those are the ones that we're most excited about and that mesh the nicest with the deep learning libraries. But you could use SciPy, you could use any out-of-the-box optimizer in SciPy. Because PennyLane's circuits are written as functions, then they slot very easily into these optimizers. So you can use any optimizer that's available in SciPy. And some of our tutorials actually use these non-gradient-based optimizers. And I know Maria's probably out there in the chat as well. You don't need to use gradients for quantum circuits if you can also think about them in terms of kernel methods. So if you use the theory of kernel methods, you can actually kind of write your optimal solution as a function of the input data, and you don't have to necessarily tune the gradients at all. So that's also one way to use it.
Oh, cool. And I'm learning a ton in this session. This is fantastic. So we have GoPaller, the user GOPALRK asks us, how would one define the capacity of quantum circuits as we define in like a classical deep neural network?
I would say that that's the question we're kind of like only just really starting to explore. So we're just kind of tickling the question a little bit. We're not kind of, it's not a solved problem. I know one of our speakers tomorrow, Hannah Sim, she's had a paper on understanding the capacity of quantum circuits. I know you can think about generalization. If you're talking about QML, you can think about how well your circuit generalizes or not. And there's a bias variance trade-off. So all of these ideas are actually on the table. I would say that nothing is settled in quantum. For me, for something to be interesting, your quantum circuit, if it's parameterized, then those parameters should have values that are reaching a point in Hilbert space that is computationally intractable for a classical computer. That's when things become interesting, is that you can reach those hard to find places in Hilbert space.
Makes sense. I mean, this question's been asked a few times now, so I'm going to have to get to it. Are those D&D books on the shelf behind you, Nathan?
They are. We have. This is real old school, 3.5.
3.5. Oh yeah.
Yeah, that goes back to undergrad days. When you and I were back in undergrad, Paul. And then this is 5e. So good eyes for everyone. If you're into D&D, we have a speaker tomorrow, Marco Cerezo from Los Alamos National Lab. He is a noted dungeon master, so definitely check out his talk.
Oh, that's good to know. A little insider information. Sticking on the sort of personal questions. So I understand that you've had a couple of run-ins with some very famous machine learning people. One almost run-in and one actual run-in. Do you want to maybe tell one of those stories?
Yeah, I mean, obviously I have run-ins every day with some of the best QML people, but these are more stories for classical machine learning people. So I have interesting stories for both run-ins with Yoshua Bengio, who's a famous researcher in Montreal in deep learning, and also Jeff Hinton. So maybe the chat can tell me which one they want to hear, Jeff Hinton or Yoshua Bengio.
Ooh, turning it over to the chat.
Yeah,
All right.
they're
Well,
both good.
we'll give that a couple minutes, and we'll go to another question while we wait for that. So I think this hopefully this is less contentious and easier to answer. Would you agree that CMYK is the only acceptable Slack theme for the vibe of QHack?
I, I don't know why I need to take a position on this. It's all about having fun, people.
I think that's the right answer. That was the right answer. Thank you, Nathan. And another one that let's tear this Band-Aid off right now. Where does the name Xanadu come from?
I'm gonna leave that to my colleague Juan Miguel on Friday. He's got a talk, PennyLane, the Untold True Story. It's a comedy show, and in that he goes into a funny story about the history of Xanadu and where the name come from. So I don't want to spoil it.
Okay, just to let everybody know, we will get to that question. Yeah, it's a very popular one. Thanks. So okay, let's see. I'm not seeing any consensus yet on what question people want or what story they want you to tell. So I'm just going to keep asking you questions.
All right.
We didn't get a lot of people starting out looking to get into this field and looking about, like, for example, like work. So like if you wanted to build up your professional profile for quantum computing jobs, how might you do that?
It's really interesting because when I was a grad student, I wanted to get into quantum computing. And the only way to do that was to get it accepted into a PhD program somewhere or a master's program or something like that. I was fortunate enough to be accepted into a PhD program in Waterloo Institute for Quantum Computing. But that was more than 10 years ago. So right now, it's really, really lucky for people who are getting into things now, because you don't need to get to that level of standing before you can contribute. There are hackathons like this. Hackathons did not exist in quantum computing 10 years ago. They do now. So you can take part in hackathons. You can skill up. You can learn all the quantum software libraries. There's tons of material available freely online. And you can really just try things out. And I think that the best way is actually just get your hands dirty, download some code, read some papers, read some tutorials, get yourself knowledgeable, and get to a stage where you can start, actually coming up with new ideas, or even if you want to, help others on the same journey you took on. It's a lot more easy now than it was in the past when I started.
Cool. Do you need any special setup for getting started with quantum coding and working with PennyLane? Special hardware or anything like this?
Just a computer with Python. So if you're comfortable with Python, which I think is kind of the easiest scientific language to learn, and it's the most broad one, I would say, as well, in terms of if you're coming from different backgrounds, you might have that as your skill set. If you're comfortable with Python, then you're good to go. And if you want to get into QML, you can check out our website. We've got tons of tutorials to help onboard you.
Very cool. So I think I'm going to pull an executive decision here and say I want to hear the Jeffrey Hinton story, just because there's that Canadian connection. And here we go. Yeah, the winner is Jeff Hinton. So there we go. Perfect.
Okay.
So let's hear it.
Sure. So Xanadu is based in Toronto, and Jeff Hinton is famously from the University of Toronto, and that's where he lives. That's where he works. He's also at Google, but they have their Toronto offices. So in the very, very early days of Xanadu, this is when we had maybe like 5 employees. We had somehow, I don't know how, our CEO convinced Jeff Hinton to come check out this quantum computing startup with 5 employees. We were in an old garment factory. So that a lot of the startups in Toronto go in this garment district and repurpose these buildings. So there was actually like some kind of strange sewing machine operation going on above us. So it was always very noisy. And you had all these really rickety floors and windows and so forth. So it's a really sketchy building. And somehow our CEO convinced Jeff Hinton to come check us out. Don't know how he managed to do it, but he convinced him. And so we were all sitting there waiting for Jeff to come. And about 10, 15 minutes go by, and it's like, oh, he's not here. Maybe he's lost. Let's check the email, see if he sent a message or something. And we checked the email, and it says no. We sent him the address. He's got the proper address. The address is 304-372 Richmond Street West. This is our old office in Toronto. So don't send us mail because it won't get to us. That's our old office. But in Canada, there's a lot of ambiguity between that dash. It doesn't have a lot of heavy lifting. So 304 was our room number, 372 was our building number on the street. And so I guess Jeff Hinton, what he did is he saw 304, and so he went to 304 Richmond Street, which is completely the wrong building. So innocent mistake, right? So I could just picture him wandering around the street looking for this building, and he can't find it. But the worst part is it was just pouring rain that day. There was just so much rain going on, and eventually we found out later that he was looking for the building and he got lost, and he didn't have an umbrella, so we got absolutely drenched. Wow. He never made it to our office to check out our quantum computing company. I know Christian has tried to reach out to him many times since then, but he's having a hard time getting his attention. But that's the story of Jeff Hinton's close brush with Xanadu in our early days.
Gee, I wonder why he's refusing your calls now after that treatment. Well, we got to get a campaign going, I think, to try to get Jeffrey Hinton to the new offices. They're much more upscale.
Easy to find too.
Yeah, much easier to find. Although we do still have that semi ambiguity. I know exactly what you mean with the unit number in front of the building number. As someone who's lived in a condo for a long time, yeah, we've all been there. Oh, some really good stories. I think we have a bit of time. I also want to hear the Joshua Bengio story. So all
right, Paul, just for you.
Executive decision, just for me.
All right. So again, in the early days of Xanadu, our CEO was trying to attract the interest of some of these big machine learning people. So he was reaching out to Joshua Bengio, and again, somehow we had convinced Joshua Bengio to take a call with us. Again, I don't know how, but he agreed to have a Skype call. So we have the date set up, and for some reason it's at lunchtime. So exactly at 12 noon. I guess we don't really get a choice in when those meetings are scheduled. We just take them when we can get them. So it occurs at lunchtime. And this is again in our old office, and this is a bit later in the company's history. So we were more than 5 people. We were maybe about 20 people, and the office was getting a bit crowded as well. It was getting noisy. It was getting crowded. It was getting overflowing. So 12 o'clock rolls around. I'm meant to have this meeting, and all the meeting rooms are taken. And I'm scrambling like, I need to, it's a very important person. I got to look professional. So I end up going into the printer room, which is it's not a meeting room at all. And it's just right beside the kitchen. So here I am on this Skype call trying to convince Joshua Bengio to, learn more about QML. And there's printer paper, printing beside me. There's people enjoying their lunch right outside the door. It was very, very stressful, but he ended up inviting us to give a talk in Montreal. So I think it went well.
Right. Maybe he felt sorry for you guys having to deal with those conditions.
Man, that's startup life. That's part of the fun.
Hashtag startup life. Yes. If you haven't seen images of the old office, I'm sure they're somewhere online. I suggest people hunt them down to check it out. It's amazing the work that went on there in those conditions. Really mind blowing. All right, well, we're going to have to move on, but this has been fantastic. Thank you so much, Nathan, for coming here, giving this talk to everybody, answering questions, sharing a little bit about your D&D history with all of us. This has been fantastic. Everybody, please stick around. We're going to be back shortly with the next talk. But first, I think we're going to go over to the leaderboard and talk a bit about the QML challenges that are happening.